In 6.2, we'll be starting a very important topic on function inverses. And we'll talk about, for some of the types of functions we've already been studying, how do we find the inverse, what does it mean, and what sort of properties does it exhibit. But before we get to all that, what's the first most important condition is that in order for a function to be invertible, it must be one-to-one. So let's go ahead and talk about what that means and look at some examples of certain functions which are one-to-one and certain functions which are not. And if we go back and think about the example of the World Series champion function example that I posited when I was first talking about functions, obviously the point of a function is a correlation between domain and range. We have something within the input, it's correlated to something within the range. Now, a very specific type of function we say is one-to-one if for each input it is connected to a unique output. And meaning that that's a way of saying that in a one-to-one function, you're not allowed to get the same output more than once, when you're using a different input. So if we were to apply that to the World Series example, like, in 2010 or in 2012, the Giants won the World Series or whatever. But if you remember back in 2014, the Giants won the World Series again. And if we were looking back at the function map, you would see that there's more than one arrow connecting to the Giants. And in the real world, a lot of times with certain functions, that's totally fine. And a lot of functions are not one-to-one. But we would just say that that is not one-to-one because there's more than one input number connected to the output. And in the World Series, the same team is allowed to win more than once. It's like once a team wins, they're not banished from the World Series ever again. But that, if that were the case, that would be what a one-to-one function would be like, where each input has to have a unique output. So if we're thinking more about mathematical functions, like say, for example, x squared is a classic function which is not one-to-one because you can plug in two different numbers into the input and get the same output. And one of the obvious examples is with a positive versus negative numbers. Like say we were to plug in 2 or -2 into f of x, for this very first example. F of 2 is equal to 4, because of course 2 squared is 4. But if we were to plug in -2, well, of course -2 squared is also 4. And that's kind of the idea that I'm trying to illustrate. We have two different inputs connected to the same output value. That is not one-to-one because repetition is not allowed within a one-to-one function. And if we look at the graph of a function which is not one-to-one, like for example, x squared looks like a parabola, of course, centered at with a vertex at the origin. Oops, let me get rid of this annoying marker. There we go. We can kind of see the fact that a function is not one-to-one by the fact that it doubles back on itself. Any function which has a turn, like polynomials of higher degree, now technically they don't always have to be not one-to-one, but often that is the case. But it's because, when we're looking at 2, we're going to get 4. But when we plug in -2, we're also going to get 4. And what we have is a repeat value. And basically what I'm trying to lead up to is what we call the horizontal line test. The horizontal line test is a way we could check to see if the graph of a function is one-to-one or not. It's exactly synonymous to the vertical line test. Remember that the vertical line test checks to see if a graph is a function. The horizontal line test checks to see if that function is one-to-one. And if it crosses the function in more than one point, we would say that this function is not one-to-one because it has repetition. As I was trying to explain, that's not allowed within a one-to-one function. But obviously, in a parabola, it's never going to be one-to-one because you have that turn, you have that arc, you have that repeat. But a lot of sometimes you could have a graph of a function which is one-to-one, like the identity function f of x is equal to x, which that's one of the simplest functions there is. Basically, input and output are the same, or what that would leave us with is a line with slope of 1 and an intercept of 0. But all linear functions which are not horizontal lines are always one-to-one, right? Because and again, if I was to use the horizontal line test, which is what I was referencing in the last example, notice that in this function, no matter where I draw a horizontal line through this function, in each case, it's only going to pass one time, and that is fine. Basically, the horizontal line test, you want to you should be able to draw a horizontal line anywhere through the graph of your function, and it should never intersect the graph more than once. If it does intersect the graph more than once, as it did right here, we'd say that the function is not one-to-one. But if it only intersects the graph once in every possible location, then it is one-to-one, and we say that this passes the horizontal line test. So, basically summary here that this first one was not one-to-one, and we say that this one fails the horizontal line test, and then this one is one-to-one, and we'd say that this one passes the horizontal line test, and this one failed. Okay, so looking at a few more, and this is kind of how you can determine if a function is one-to-one. If you're looking at a mathematical function, is, well, you can use the graph. So you could do sort of like I did above, where I was like, well, I could try to find two different values that cause repetition to see if it's one-to-one or not. But you could always just look at the graph and use that to make the determination. If you're not sure what it looks like, you can always even use your calculator. Like, let's say we wanted to know, what about the square root of x? How do I know if that is one-to-one? Well, I could start by graphing it in my calculator, or, obviously knowing what the basic shape of your mathematical functions looks like is always helpful and important, and it just helps us know the properties of the function. But the square root function looks sort of like a half rainbow or a half arc, and really the square root is also a parabola, much like x squared. It's just sideways, and it's only half of one. And that being said, if we were to draw a horizontal line anywhere through this, no matter where we would draw it, it would be one-to-one. And if I were to create a small sketch of this, square root of x looks something like that. We'd say that this passes the horizontal line test, and again, that means that this one is also one-to-one. Another thing you might be wondering is, well, how do I know if the graph ever goes completely horizontal? Because in a graph that looks like the square root function on the right, this could be something you were thinking about. Well, what if it actually were to level out and turn into a flat line? And obviously that's possible depending on, the curve, but with mathematically defined formulas like the square root of x, you could think about it that way too. Well, if I plug in, say, 10 or 20, is that going to ever give me the same number? And since it's uniquely defined by the square root of a number, the square root never has there's no two different numbers that give you the same square root. Every number has a unique square root. Every unique number has a unique square root, and that's another way of thinking about why that's one-to-one. But basically, it's going to keep growing over and over, like forever. It has no limit. It has no horizontal asymptote because it's an unrestricted function. And even if a function has a horizontal asymptote like 1 over x, and this one we've looked at the graph previously, but it looks something like this, where on the upper right hand side we got the reciprocal nature, but one of our very basic most reciprocal functions. This one would have a horizontal asymptote at x equals 0 and a vertical asymptote at y equals 0. But that being said, it still is one-to-one, even though with the horizontal asymptote, as it moves to the right, it's going to get smaller and smaller and smaller and get closer and closer to the x-axis, or the line y equal to 0. But this is kind of the thing is, well, does this pass the horizontal line test because it has a horizontal asymptote? But every single value is unique. Even if it has a horizontal asymptote at 0, it still will be one-to-one because it's getting closer and closer and closer, but it's never actually touching the asymptote, and it never actually repeats itself either. So it's kind of, this was sort of a, there's a lot of mathematical paradoxes, and this a few hundred years ago was a area of a bit of contention, saying, well, can you continuously get smaller and smaller and smaller even though it's never actually going to reach 0? Is there an end to this? But anyways, yeah, this one is one-to-one, passes the horizontal line test. In other cases, like say for example looking at a baseline cubic function, usually cubic functions are not one-to-one because the polynomial has multiple terms in it. But when x cubed is just by itself, on the right side it looks like this. And if you recall, x cubed by itself was an odd function. Now, odd functions are not necessarily one-to-one, but in this case it actually is, because as we're moving from left to right, it kind of has a little bit, instead of really truly turning, it kind of has a bit of a bend at the origin instead. And it actually is one-to-one, it passes. But another way you can remember is even polynomials, even degreed polynomials are never one-to-one. Odds can be, but still not necessarily. But when it's just x to the power of n, when that is odd, those actually will all be one-to-one. But when you start throwing in other terms, that is when you'll get multiple x-intercepts. And of course, if a polynomial has more than one x-intercept, it can't be one-to-one because it fails the horizontal line test. So it has to be very, very specific cases. Anyways, and then the absolute value function is never one-to-one either, much like x squared, because whether you plug in positives or negatives, you always get repeated values. And if we were to put a negative out in front, that would just make it upside down, and we'd have a graph that looks something like this. Or of course, if you're not sure what something looks like, you can always go into your calculator and graph negative absolute value of x. And if you recall, the absolute value is within the math menu if you're trying to figure out where that is. But we could always look at the graph and see, okay, that does not pass the horizontal line test. Just like a parabola, if I were to put a horizontal line through it, it would cross it more than once. That is not allowed. So we'd say that one is not one-to-one. Cool. And all that being said, any functions which are not one-to-one are not invertible functions. Kind of going back to what I was saying at the very beginning. In order to have an inverse, they must be one-to-one. And that is one of the main reasons why this is so important. And I'll kind of talk more about why when I start talking about inverses in the next video. But the last thing I wanted to say is, how do you prove something's not one-to-one? Because this is kind of like an anecdotal process where I'm just sort of using the graph to say it, but I've not actually proved anything. And this is going back to, if you look in the book, how a one-to-one function is defined. And it's often defined by, well, if f of x1, basically saying if we have two different x1, let's just say that x1 does not equal x2, two different values. If we plug those in, f of x1, that always has to produce something different than f of x2, meaning that, no matter what I plug in, it's always given me different answers. It'll say something like this. Because if f of x1 equaled f of x2 for different values, that would imply that we have some repetition, or again, that it would be a violation of the horizontal line test. But for each pair of different inputs, we would have to get different outputs. And basically, you can contradict this or prove that something is not one-to-one by basically providing a counterexample, finding two different x values which violate this, basically where you have an equal output. It was kind of like I said at the very beginning with x squared. Both positive 2 and negative 2 give me the same answer. That's not allowed. And so, if I was trying to do it for some random function, what I could do is basically apply the horizontal line test and figure out where that is. Like, I could go ahead and graph 2x squared plus 4x plus 2. And then look for a repeated value. And for example, it looks like maybe at 0, I'm going to get 2, and maybe at negative 2, I'm also going to get 2. So I could just, find some values. I could even just plug random numbers in until I find a duplicate. That sounds a little bit tedious though, but f of 0 is equal to 2. F of negative 2 would be equal to 2 times negative 2 squared plus 4 times negative 2 plus 2. Actually, that will not be 2, will it? Oh no, that will be, because this will give me 8 minus 8 plus 2, which is 2. And basically, as I said, I would be looking to find two different x values. So we could say that x1 does not equal x2 here. But what I get is f of x1 does equal f of x2. And that's not allowed. I'm not allowed to have that duplication.